Picture two equally intelligent developers. You give them the exact same dataset, the exact same codebase, and the exact same model. One of them looks at the output and says, "This looks amazing, ship it." The other looks at that identical screen and feels a creeping sense of dread, wondering what kind of nightmare hides in the edge cases. Both understand the math. Both are perfectly capable of building the system from scratch. The divergence comes from a specific way of reasoning that develops after spending years around probability and quantitative systems, a set of habits that changes how they interpret every number on the screen. Human brains are wired to crave certainty. In everyday conversation, we naturally gravitate toward a single point estimate: the expected return, the predicted outcome, the average result. Extracting one solid number from a chaotic dataset creates a false sense of security, making massive uncertainty feel neatly manageable. But treating those isolated numbers as absolute truths is incredibly dangerous. It papers over the volatility, the hidden assumptions, and the potential failures that generated those numbers in the first place. Surviving a complex system means abandoning the search for a neat final answer. It requires adopting the adversarial cognitive architecture of a quantitative thinker. The first step in the quant workflow is learning to safely observe massive complexity without freezing up. When a system has thousands of intersecting variables, calculating an immediate outcome is impossible, so you break it down through systematic decomposition. You isolate exactly where information enters the system, where the random noise occurs, and which specific components actually dictate the final result. This process relies heavily on something highly unscientific: human intuition. A seasoned quantitative thinker doesn't ignore their gut feeling. Instead, instinct serves as an initial hypothesis for those isolated components. Intuition spots a subtle pattern. Formal mathematics rigorously stress tests that pattern through simulation. The results are fed back, sharpening the gut feeling for the next problem. A quant's very first move is never to calculate a final answer. It is to build a structured framework where human instinct and hard data can safely interact and refine one another. Once the system is broken down, the focus shifts to translating the unknown into something measurable. This is where the danger of relying on averages becomes glaringly obvious, and where attention must shift toward the entire distribution of possible outcomes. This chart shows two distinct systems sharing the exact same expected value. One strategy delivers small, steady gains over time. The other constantly experiences massive fluctuations. The mathematical average is identical, but living through the reality of those systems would be vastly different. This practice is called structuring uncertainty. Instead of waiting for perfect information, quants map the entire range of possibilities and assign relative likelihoods to each scenario. Every prediction exists within a strict boundary of rules. In probability theory, this is formalized as conditional probability, the measure of the likelihood of an event occurring, given that another specific event has already occurred. It means no mathematical conclusion is absolute. It only exists within a temporary set of assumptions. Real-world markets evolve. Data distributions drift. A model operating flawlessly today will quietly degrade the moment the underlying conditions shift. Quantitative thinkers never view the future as a dark void. They view it as a carefully mapped territory of probabilities, which is heavily dependent on temporary, fragile conditions. This leads directly into the final, most aggressive phase of the workflow, the adversarial mindset. Once a system is built, the goal immediately shifts to tearing it down. You start by examining the extreme cases. You push inputs to absurdly large numbers, inject impossibly small values, and stress the system until the underlying logic finally snaps. This chart shows a standard probability distribution, but the real focus is here, at the absolute edges. The most catastrophic damage in finance and machine learning rarely happens during normal operation. It almost always occurs during rare edge cases sitting in the distribution's tails. When a new solution appears promising, the natural reaction isn't confidence, it's deep suspicion. A quant interrogates their own work, actively hunting for hidden dependencies and fragile assumptions, rather than trying to defend the model. True confidence in a system doesn't come from a flawless initial test. It only arrives after you have spent days actively trying to destroy your own creation and completely failed. Let's go back to those two developers looking at the identical screen. The one who felt a creeping dread wasn't being pessimistic. They were looking past the top-line number, seeing the fragile conditions and catastrophic tail risks hiding right behind a seemingly perfect average. The developer who demanded a final answer walked straight into a trap. The one who viewed the data as a structural framework spotted the fatal vulnerability before it could do real damage. This cognitive engine appears in data science, engineering, and research. It offers a rigorous way to evaluate any environment where information is incomplete and the stakes are high. Uncertainty is the default state of reality. We cannot completely eliminate it. We cannot predict the future with perfect accuracy, and we certainly can't sit around waiting for the unknown to simply pass us by. Adopting these habits means letting go of the need for absolute certainty. Numbers stop being final answers. They become invitations to understand the hidden architecture of the systems that generated them.